Assalamualaikum and a very good morning. Today we are from Group 4 want to present about electromagnetic sensing on agriculture. So before we start, we would like to introduce ourselves. My name is SHAH.
My name is XIAN.
My name is NOORSYATIRAH binti OTHAMAN. And my name is SYAFINA binti
Okay, so let's go more deeper about this sensing element. Firstly, we would like to see the application in agriculture industry based on electromagnetic sensing element. So one of the application is the electromagnetic wave as tools in the field of agriculture have been used in many applications such as remote sensing, imaging, quality sensing and dielectric heating in a pre-harvest or post-harvest environment. However, the goal here is to discuss about applications which are directly related to the main electromagnetic wave effect, which is warming. Among variable methods applicable in the agriculture section, radio frequency power has been known as physical thermal method. In this method, the general idea is the same as heating food products to kill bacteria. It can be used to disinfect various food and non-food materials, including soil. On the other hand, there are applications of using radio frequency to measure soil parameters and soil salinity as well.
Next, here are some devices that uses the electromagnetic sensors. The first device is the EM38. There is the electromagnetic sensor in this device. Component of the EM38, it contains two coils of wire, one for creating a magnetic field, which is the transmitter coil, and the other for sensing an external magnetic field, which is the receiver coil. Function and the operation is still the same as we discussed before for the electromagnetic sensor. It uses the same principle. The functions of the EM38 are to determine the soil parameters, to select the soil sampling points, and it is used in agriculture and archaeology. This is the video of the operation of the
calibrate the EM38 Mark II. Basically, the first thing we've got to check is what our battery's like, and you can see on here the battery's 1300, so anything from sort of 700 up is plenty of charge. What we do then is basically put it into just a normal operating mode, place it down on the ground and go and get your stuff ready, start getting all the rest of the gear ready so this thing warms up a bit, gives it 5 or 10 minutes of warming up. You can see that the numbers there, this is the in-phase reading, that's the quad phase reading. This is the one we're interested in working on, but we need to make sure that the in-phase up here is around 0. So there we go, a slight little adjustment on that in-phase one affected that. Therefore it's now somewhat close to 0. This here we can see we've got a quad phase reading of 12. If we now turn that up into the vertical mode, that's reading sort of 16, or it's varying a bit. You can see it's just on -2, just wind it up a little bit, you've got close to 0. This one here, same thing, that's a reading of 4. That's a reading of 5. So we need to just 5 minus 4 is 1. So we just dial our little quad phase reading back to 1, back there, and then this should be 2. So this reading is always double what this reading is here in horizontal mode. So now that's properly calibrated. Make sure you flip the little locks over, turn it back. It doesn't really matter what that's on, but I usually just leave it on the 1 meter setting. And then you've checked your battery, so that should be right. You put it then over in the box, and we've got the sled here with the what we call the coffin, I guess. So we lay that in there, nice and snug, and basically as low to the ground as you can possibly get it. And then you can go and set up your Bluetooth on your logging screen.
Next, this is another application of it, which is the precision agriculture, which is known as PA. PA, it includes the use of yield maps, other spatial information, and input control technologies. So in these functions, it uses electromagnetic sensor to sense and determine the information of the soil profile change. This is to enhance the agronomy to the paddock variability. So you can see here there's a figure there with different color. The zone 1, from the result detected by the electromagnetic sensor, zone 1 is low clay percentage, moisture percentage, CEC, and the average pH of it is 4.5. So this zone is a low yield zone. So secondly, which is the green color zone, the standard management practices will be continued to yield to higher the yield. The third one is the blue color zone. This zone can, as you show here, the blue color can hold more water, but it is high solidity and magnesium. So some measures need to be done to reduce it.
I want to continue with 3 other methods, including which is ionization, radiation, cool treatment, and conventional heating. For the first, in ionization, radiation, the main problem is that it is not possible to shut off the radiation after ending the treatment. In addition, there are still some roadblocks to using this ionization radiation. For the second, cool treatments are not a complete method due to high price and relatively long required time. And for the third, conventional heating. This method originates from the fact that this kind of heating warms both pests and the agriculture products similarly, which may destroy products' quality. So to overcome this problem, some modern techniques such as genetic treatments, ultrasonic wave, and the electromagnetic treatment have been suggested in the literature.
Hi, okay, we move to the next part, which is one sensor design for agriculture. So we choose soil moisture sensor, which is this sensor is a technology commonly used indirectly measure volumetric water content, including the FDR, which is frequency domain reflectometry. This FDR is functioning while the dielectric constant of the certain volume element around the sensor and measure the operating frequency of oscillating circuit. This sensor also include the time domain transmission (TDT) and time domain reflectometry (TDR). And this transmission function as a dielectric constant and for certain volume element around this sensor. And soil resistivity, measuring how strongly the soil resists the flow of electricity between these two electrodes. And the galvanic cells, which is this one, the galvanic cells, is to measure the amount of water presence. Soil moisture sensor measure the volumetric water content in soil, and the relation between the measured property and soil moisture must be calibrated first to know the soil type, temperature, and electric conductivity. And soil moisture sensor typically refer to sensor that estimate volumetric water content. So I have a video to show you.
Hello, my name is Walker Mitchell and I'm an applications engineer here at ON Semiconductor. Today, I will be showing how our portfolio of battery-free, wireless, smart passive sensors can be used in digital smart farming applications, where traditional sensors are not practical due to their wiring or battery requirements. Our newest smart passive sensor tags, or SPS tags, separate the UHF antenna from the location of stimuli detection, enabling soil moisture measurements underground. Analyzing the soil moisture content across large areas of farmland will allow farmers to optimize irrigation techniques and minimize the overwatering costs. In order to collect the data from all of the smart passive sensors placed throughout the farm, a mobile UHF reader is required. Attaching the reader to a drone is a natural fit due to the increasing use of drones in agriculture for both imaging and spraying. The mobile UHF reader can then be programmed with a flight path to read the sensors of interest throughout the entire farm. Once the data is collected by the drone, it can be synthesized to determine which portion of the crops are receiving optimal moisture levels and to adjust watering schedules and locations accordingly.
That's all from us so far. I hope the info we talked about just now will be a good info to all the students who's taking this measurement system. And that's all from us. So thank you.